Franz, for those kind words. It is indeed a long time since Marseille, but a very pleasant time. Thank you. So I want to talk today about formulating problems in real algebra and geometry. And I want to start by looking at a classical problem, which is... I should first say I'm very grateful to both my colleagues in Bath, Russell Bradford, Matthew England and David Wilson, who've been working with me on this problem for some years, to Chris Brown and to Scott McCallum, who've both visited Bath and given us much insight. So I'm going to start with a classic problem, which is our quantifier elimination. And so the Q's will be either existential or universal quantifiers. Then the problem of quantifier elimination is if you're given some formula phi, capital Phi, which contains a bunch of quantifiers, and then quantifying some sentence little phi, to produce an equivalent formula which doesn't have the quantifiers in it, which is why we call it quantifier elimination. So much is obvious. And so, of course, this will depend only on x1 through xk. And in particular, if k is 0, then psi is just either true or false, and we've got a decision problem. And a lot of things can be expressed as quantifier elimination problems. For example, here is a statement of Goldbach's conjecture. For all natural numbers greater than 1, there are 2 primes, p1 and p2, such that twice n, so every even number, is the sum of 2 primes. And what I said, it's a prime, but that's not a quantified statement. Oh yes, it is. Say m is a prime, says for all p for all q, if m is pq, then 1 of p and q is 1. So that's a statement with 7 quantifiers, 1, 2, 3, and 2 here and 2 here. In fact, you don't need that. You can use the same quantifiers p and q in both the statement p1 is in p and p2 is in p. So in fact, you can state it in five quantifiers. So if I could do quantifier elimination, I could solve Goldbach's conjecture. And in fact, quantifier elimination over the natural numbers is impossible. Not just very difficult, it's actually impossible, which is one way of stating Matusiewicz's or Robinson's result. However, earlier, Tarski had proved that for semi-algebraic statements, we say semi-algebraic because it involves inequalities as well as equalities over the reals, then it is soluble. That result was due to Tarski. Good news is it's soluble. The bad news is that its complexity is indescribable. I use that word very technically. You can prove that there is no primitive recursive function that bounds the complexity of Tarski's method. So it really is indescribable in the technical sense as well as the colloquial sense. That's Tarski's method. Collins in 1975 produced an alternative method. So phi is my statement in variables x1 through xn. Let Sn be a set of all the polynomials involved. And let's say that's got m polynomials, degree at most d, and of course n variables. And then Collins said, from that, produce a set Sn minus 1, which will be in n minus 1 variables. They'll be proportional to m squared such polynomials that have degree d squared. And you keep going. You then produce Sm minus 2, which has roughly m squared squared polynomials, a degree d squared squared, n minus 2 variables, and so on. And you end up with a set in one variable of quite a lot of polynomials of quite a high degree. But at least I've described it, which is an improvement on where we were before. Having done this, we now have polynomials in one variable over the reals, which are things we know about. So we can actually isolate all the roots of this set of polynomials, by which I mean I can say, here is a root of polynomial 17, and it is to the left of that root of polynomial 16, and to the right of that root of polynomial 42, and so on. So I understand exactly what's happening on the real line based on these polynomials. And then over for each root and for each gap between two adjacent roots, I isolate the roots of my set S2. And I continue until I end up with isolating all the regions of Rn on which all the polynomials in Sn will have, and this is why we constructed the various intermediate sets the way Collins tells us to, such that each Sn has a constant sign. It's either positive or negative or possibly zero on each region of Rn. And therefore, if each Sn has a constant sign, phi n has a constant Boolean value, true or false, on each cell. And then we evaluate the truth of the whole statement, the quantified statement, on each region of x1 through xk space, and that will tell us, and then the true cells tell us what the answer is. That gives us the formula phi. And the complexity of this is clearly proportional to m and d to the power 2 to the roughly n, big O m. And in fact, Collins does a very detailed calculation and shows you it's 2m to the power 2 to the power 2n plus 8, and so on. Well, not good, but describable. As I said, yes. Now you can actually analyze the step n plus 1, the step that that solves R1. If you do a better analysis of this, you can actually reduce that 8 to a 6 and that 6 to a 4. Which doesn't look very impressive, does it? Well, wait a moment. I claim it is. Because after all, I've taken the fourth root of the complexity. Which is actually quite impressive. Yeah, if I came to you with an ordinary algorithm and said, I can take the fourth root of its complexity, you'd be impressed. Now, in fact, having said which, this work was very largely a work to improve the analysis, not the actual running time. But the point is, if you're in doubly exponential space, you can make significant improvements, but you're still in doubly exponential space. Indeed, quantified elimination has to be doubly exponential space. 2 to the 2 to the n minus 2 over 6, or if you try a bit harder, the same sort of trick as I used with Goldbach when I said I needed 5 quantifiers, not 7, you can make it n over 5. And this is in the dense model of polynomials, where a polynomial of degree d has d plus 1 coefficients. And that's perhaps artificial, because that's not how algebra systems actually store polynomials. I can write down the polynomial x to the million minus 1, and I don't store 999,999 zeros. So this complexity result is perhaps not quite what we'd want to say. Nevertheless, in terms of complexity, we're 2 to the 2 to the theta of n, because I've got an upper bound, a lower bound, both proportional to n, which of course is not the same by any means as theta of 2 to the 2 to the n. It's a big problem in complexity theory here. I can make major improvements, as we saw, without changing the fact that it's 2 to the 2 to the theta of n. Now, the key idea is in fact due to Joost-Heinz. Suppose I've got some formula phi n, which is yn equals fn of xn. If we consider phi n plus 1 to be, there exists a Zn such that for all xn and yn, this Boolean combination implies phi n, then what I've done really, because I've got the or here, I've got yn plus 1 is fn of xn plus 1. So given any formula, I can put this constant length prefix on it, and I've iterated the formula. So we applied this to a very simple sawtooth function, And you get, of course, very rapidly increasing sawtooth. So F0 is a sawtooth, F1 is a double sawtooth, F2 is a 4-fold sawtooth, F3 is a 16-fold sawtooth, and so on. And then you get a set with 2 to the 2 to the n isolated points. And then that takes doubly exponential space to encode in practically any form. The dense form, as I said earlier, the sparse form, because to get that many real roots you need that many non-zero coefficients by Descartes' rule. And in fact, even in a factored form, you still can't get any better than that. So that's rather more worrying. That says that in terms of the technology we use in computer algebra systems, we're forced to have a doubly exponential space bound and therefore time bound. However, let me just say something else here. So our construction, as we use it here, puts these blocks, exists for all. We put a bunch of these in front, and for every 3 quantifiers, I've got 2 alternations. I change my mind. Exists, a couple of for alls, exists, a couple of for alls, and so on. In fact, alternation of quantifiers is a very powerful concept. It's actually also quite recent. Cauchy never understood it. If you think about it, in analysis, the difference between continuity and uniform continuity is that uniform continuity has more alternations. The fact, I believe, which was discovered by Weierstrass. So now let A be the number of alternations. Then there's a method due to Neuer-Fitchas, which is a pseudonym, Juste and I forget who else, which says that the sequential cost of doing quantifier elimination is singly exponential in n, but doubly exponential in the number of alternations. So in fact, according to this theorem, it's really the alternations that hurt you, not so much. Well, not so much, only singly exponential in the number of quantifiers themselves. Of course, the example we had, we've got 2/3 as many alternations as quantifiers, but other examples might not. As we said, yeah. The trouble is, I know of no implementation of this method. It's sat on the shelves of the theoreticians at the moment. But it does mean that cylindrical algebraic decomposition, the way I've described it, is not necessarily the best way. Because cylindrical algebraic decomposition will always be doubly exponential in n. And this method, of course, is taking account not just of the polynomials, but of the quantifiers. And a lot of people have done experimental work around this, trying to say, well, if we know what the quantifiers are, can we do better? Which comes down to asking ourselves, let's take more care over what the problem is. So if we knew what the problem is with the quantifiers, and we could say our quantifiers correctly, we might, if we had an implementation of this method, which we don't have, be able to do better. So that's worth asking ourselves, what exactly is the question? Now, it turns out that the order of the variables is sometimes critical. Here's a rather messy looking polynomial, which in fact is, you've got x0 minus a half squared, y0 minus 2 of x0. It's actually the same sawtooth I had a couple of slides earlier, just expanded and encoded. If I eliminate in the order, I first eliminate z1, first eliminate x, then y0, then alpha, then x0, and so on, and the last variable I eliminate is a, then I get a cylindrical algebraic decomposition with at least 2 to the 2 to the n cells. And that's essentially a consequence of the previous theorem. If I eliminate in the opposite order, I have 3 cells. So depending on which way you eliminate. Now, of course, if you want to do quantifier elimination, you have no choice on the order. Well, If you've got total alternation, you've got no choice. If I've got, here I've got, that variable has to come last. These two can come in either order. Then that variable has to come next, and so on. If I had complete choice, I'd have a difference in complexity between constant and 2 to the 2 to the n. Conversely, we can also show there are problems which are doubly exponential in every order. So I can give you problems which look rather similar. One of them is extremely hard, however you look at it. One of them is hard if you look at it one way, and very easy if you look at it another way. So if we can choose the order, or can choose something about the order, how on earth do we choose the order? So I give you a problem, you look at it, you say, I can do this in any order. Which order should I do? Good question. There are various heuristics. One that comes to mind is for sum of total degrees. You take all n factorial orders for your n variables. You would say n factorial orders. That's, from my point of view, that's only singly exponential. Remember, I'm staring at a doubly exponential problem. So for me, singly exponential is cheap at the moment. You perform steps 1 to n. You measure the sum of the total degrees, and then you choose the best one, and you do the rest of the steps for that best one. Well, okay, that may be a good idea. A better idea might be what's called the greedy one, which is due to Doltzman and so on. You do step 1 for each variable in turn. You've got n choices. Measure the SOTD, pick the best one, then do step 2 for any of the n-1 variables, pick the best one, and so on. So rather than doing all n factorial, you do n choices at the first level, pick the best one, n-1, and so on. This is quite good. The only trouble is you often get ties. You get the same SOTD in more than one variable. A heuristic we introduced last year is the number of distinct real roots. And that's important because I pointed out for step n+1, you isolate all the real roots. 2 polynomials might have the same degree d, but one polynomial might have d real roots and one might have none. If you've got no real roots, then isolating them is easy. So this counts the number of real roots. What we at Bath tend to do is we tend to use greedy SOTD, but use NDRR as a tiebreaker. There's also a very simple heuristic due to Chris Brown. So that references to his lecture notes as an ISAC tutorial, which shows how valuable ISAC tutorials are, which says you eliminate the lowest degree variable first, and he has some quite good tie-breaking rules and so on. And it is surprisingly effective. I've just been talking to some people at Cambridge, and Zhongyang Huang there has been applying machine learning to this problem as a meta-heuristic, and her results, which I only saw last week, are very encouraging, but they're very preliminary as well. So what happens in practice? Here's an example. I want to know whether a quartic is always positive. And I've eliminated the x cubed term, which you really want to do that, by the way. This problem cannot be solved if you actually keep with current technology, if you keep the x cubed term in. So that's another example where you have to ask the right question. You can perform a Chin-House transformation, kill the x cubed coefficient, and you must do so. Then there are 6 possible orderings for P, Q, and R, because those are 3 variables. I have them in any order. I must eliminate x, but the others I do in any order. And the SOTDs are 54, 50, or 66. If we take the 2 with SOTDs of 50, I said SOTD often ties. They actually produce a decomposition with 417 cells in half a second or 1.5 seconds. Of those, some number of cells are true, and we can solve the quantum elimination problem in 0.89 seconds or 2.5 seconds. If you choose the ones with an SOGD of 54, you get slightly more cells, but much more time. And notice again that though the SOGD is the same, the time differs quite a bit. And for the other two orders with a bigger SOGD, they actually ran out of 5 minutes compute time. So there's an example in practice where the order really matters. Now, we can actually do better than the straightforward Collins method I described earlier. McCallum introduced the idea of equational constraints. If your formula is f equals 0 and phi hat, then you need only consider what happens when f equals 0 is true. All the rest is irrelevant. Now, this means the first projection step produces O of m polynomials, well, whoops, that should be O of m squared, sorry. And the complexity then, well, we just take that 8 down to a 6. Again, that doesn't sound very much, but just as I said earlier, that's actually a very important difference in both theory and practice. Now, this actually gives you an interesting question. Suppose my problem is that f1 equals 0 and g1 is less than 0, or f2 equals 0 and g2 is less than 0. This doesn't look like that. But it is actually. I can write it as f1, f2 equals 0 and all this lot. f1, f2 equals 0 doesn't add anything because either f1 is 0 or f2 is 0. So that looks like a stupid rewriting. But it's not. So I've now introduced an equational constraint. And my complexity does indeed drop by 2 here, but the degree of f1, f2, of course, is bigger, so in fact I lose slightly there. Nevertheless, in practice, this is well worth doing. Ask a different question, get a different answer. In terms of time, at least. Obviously, you'll get the same true-false answer, but in terms of time, it'll be quite different. So you might want to ask a different question. Again, should you ask a different question? All we have at the moment are various heuristics. Actually, I have a very simple question, a very simple heuristic, which says if you can write it with an equational constraint, always do so. It seems to be almost always worthwhile. There is a technical side condition. Occasionally, it can say to you, the McCallum system can say to you, no, your problem was not well oriented. I can't tell you what the answer is. It doesn't often happen. Notice it's not telling you the wrong answer. It's saying, whoops, I can't answer your question. In fact, we can do better than this. We can ask ourselves, take the same problem as before. I can say that, wait a moment, when f1 is 0, I'm only interested in g1. So, and then when f2 is 0, I'm interested in g2. And then your first projection set is these 5 polynomials, and we actually omit 5 other polynomials. Essentially, this gives you all of the advantage of equational constraints, and in fact, you don't need to introduce that polynomial f1, f2. So in fact, what you get is you get the benefit, but not the disadvantage. There's still the technical side condition of well-orientedness. Well-orientedness is one of these things that happens with probability 0, but you always fall across it in practice. You often, not always, you fall across it in practice more often than you ought to. We've actually just been working with the team in Western Ontario and China, and we think we can remove this condition and put many other improvements by combining our work with the work on regular chains. That's still work. That's been submitted, it's work in progress. This doesn't solve all the questions. Suppose I had this one. I've got two equational constraints. Which one do I prefer? So here we have some examples. So S is the SOTD, N is number of distinct real roots. So these are 8 different problems. Each row is a different problem. I couldn't fit the problem names on the sheet here. They're in our paper. So for here, the first problem, if I choose the first equational constraint, it takes 5 seconds. If I choose the second equational constraint, it takes 5 seconds. If I choose the third, it takes 1.3 seconds. And that's the winner in terms of both the SOTD and the NDRR heuristics. So the heuristics will tell you the right answer here. In fact, heuristics tell you the right answer most of the time. The only one they don't is the third problem here, where my heuristics, again, both of them in this case, say go for constraint 2, and the real winner is constraint 3. The only thing I would say here is, in fact, the difference isn't that great, as it were. Whereas if you look at the next problem, the right one, as told by heuristics, is under 4 seconds, and the wrong ones are over 20 seconds. So the heuristics don't always tell you the right answer, but as you see from this example, and our experience is much the same, if they're wrong, they're, as it were, not very wrong. We don't have examples where the heuristics give you a massively worse answer than the best answer. Yes. I have a problem here. Here's a different problem where I'm considering 2 Boolean formulae, phi1 and phi2. I want to decompose with respect to both of them, and phi1 has 2 equations in it and phi2 has 1, and this is in x and y only, so I can actually draw you diagrams. The best solution prefers f1, then h, then f2. So f1 and f2 are these 2 circles, here and here. There's a circle here, well, oval here, and oval here. We've got this parabola, and we've got the other curves. Dotted curves are the g's, the inequalities. And we decompose R2 like that, and we have various regions. My student says there are 57 of them, and I'll believe him, I think. That's the best solution, in the sense that it's the smallest description we have of R2 on which both those Boolean formulae are truth invariant. We have others. So that was F1, H, F2. If we take H, F1, F2, we get 75 cells. You can see that it's slightly more patchy. I'm not asking you to count them. In fact, that's, as it were, what you get if you push this straight into the software as it was described earlier. Slightly different variant, and then a couple more. If you say I just want F1, you get 117 cells. If you just identify H, which is perhaps the most obvious thing to do by hand, actually, you get 163 cells. So my worst case is 163. My best case is 57. That doesn't sound very much, but we're in R2, which is all I can do for drawing you pictures. Of course, we really want to work in higher dimensional spaces, but I can't show you the pictures. There are other things you can do what we call Gröbner reduction. Or the equalities. you can of course construct a Grosvenor base from, and you can use that to reduce the inequalities with respect to the equalities. And again, if you notice, the best truth invariant CAD took 0.8 seconds. After we did Grosvenor conditioning, we'd get down to 0.095, and so on. Again, we highlight the best one, and again, the heuristics tell us the right thing. If we swap the order of the variables, again, we get different, but not that different results in this case. That's because we're only in 2 variables. If we have more variables, typically the effect of variable ordering is much more substantial. Okay. Now, robot motion planning, often called the piano mover's problem. You've got an object that you want to move through space, can be reduced to cylindrical algebraic decomposition. This was a landmark paper of Schwartz and Charrier, 30 years ago, said it can be reduced to cylindrical algebraic decomposition. Okay, great. Well, maybe not that great, given what I showed you earlier. So let's consider a simple problem. So let's not do the piano mover's problem, let's do the ladder mover's problem. Let's do the ladder mover's problem in 2 dimensions. I've got a right-angled corridor, and can I get the ladder around the corridor? Which is about as simple a problem as you can think of. And when I was first lecturing on cylindrical algebraic decomposition, I came across this Schwartz-Charrier paper. I said, okay, let's take a simple example, let's do it. I couldn't do it. I ended up, remember that cylindrical algebraic decomposition, you start out with your original equations and keep projecting them. I ended up in R1 with polynomials of degree 801, but not one polynomial. You get lots of polynomials, remember. Total degree is 801, but I had lots of polynomials. I think I had 34 polynomials from memory. I could isolate the roots of each of them. What I couldn't do was solve the problem which roots of which polynomial interlace with each other. I could isolate the roots separately, but not together. I just ran out of computer time. I think I left it running for the weekend and gave up. That was a long time ago. Computers have got faster. We've got tremendous algorithmic improvements in cylindrical algebraic decomposition and in the underlying problems like real root isolation and so on. So things have got a lot better since then. Well, no, they haven't. It's still insoluble. We tried it at the end of last year. We still couldn't solve it. Using the Schwartz-Charrier formulation, using today's hardware, which is 1,000 times faster than it was in 1986, and using all the advances in CAD technology and so on. It's still insoluble. And you must think, looking at it, that if you can't solve that problem, what can you solve? That is about the simplest problem there is. Now, I should point something out here. It looks like a 2-dimensional problem. It's not really, because you've got 4 dimensions. You've got the positions of this You've got the positions of this end and the position of that end. It's really in 4 dimensions, is the point. You've got the 2 ends of a ladder, because if I tell you where this end of the ladder is, the other end still could be anywhere on the circle. So in fact, I've got 4 variables, x1, y1, x2, y2, if you want to put it that way, and the equational constraint of the length. An equational constraint doesn't help. As you can see, I can't solve it today. Nevertheless, it really is, and this is the important thing to point out, a 4-dimensional problem, not a 2-dimensional problem. Okay. So, almost 30 years of hardware and software haven't helped us. So I challenged my students with this one, and David Wilson came up with a different formulation. So this is the same problem, but he said, let's not do it the way Schwartz-Charrier did. Let's write down a different set of equations. Obviously, it's the same problem, but a different formulation. So basically, 4 things can go wrong. You can't put the ladder here, you can't put the ladder here, you can't put the ladder here, and the trickiest one is you can't put the ladder here. Both its ends are valid, but the middle is not. In fact, notice I said that you can't put it here, you can't put it with only one end outside this wall either. So the true construction of this problem is going to be the length constraint, and we're not in A, we're not in B, we're not in C, we're not in D. So this is a very different formulation of the problem than the one Schwarz-Scherer used to reduce it to a cylindrical algebraic decomposition. It's still a problem in 4 dimensions, x1, y1, x2, y2. It's just a different set of equations describing the same problem. And this one is soluble. 5 hours of CPU time, and this is the problem. It's a 4-dimensional problem. We actually get 285,000 cells. And this is the real problem. We saw what happens with the behavior on N, and that's what happens in practice. Number of cells. My previous slides, I had 57, 165, and so on. That's what happens in reality. You get hundreds of thousands of cells. And if we could solve, which we currently can't do because the theory is a bit lacking, the adjacency problem, we would have a complete solution to the cylindrical algebraic decomposition problem. I'm still not very impressed with 5 hours, I have to admit it. But, 5 hours is a lot better than insoluble. I asked my students, well, what does it look like? And they said, we haven't got 4D glasses, which is a fair comment, of course. So what happens if you take a 2-dimensional projection of the CAD? Oh, sorry, I should have said that is actually the solution formula. Which is not very enlightening, but that's what computers are for. They're there to process this sort of thing. What happens if we actually look at a 2-dimensional slice of this problem? And the answer is it looks like that. So here we've got the actual corridor, and here we've got all the various lines and so on that are used in R2. This is a 2-dimensional slice. Above each cell here are partition R3. Above each of those cells are partition R4. So this is what R2 looks like. And you can just see the number of cells in R2. And so this is the original corridor. This line is the line you get by taking one ladder width up from this here gives you along here. So that's obvious. And one ladder up from here gives you this line, and so on. And similarly, the two of the lines here have those two are the same meaning. And then you can look at some of these curves. This curve here is the curve you get as you try to pivot round here. But you look at some of these other curves, and you ask yourself, where on earth does this one come from? And also you see curious artifacts. So this curve is I think it's a conchoid. We've got another conchoid here, but it's not complete because that part is outside the projection. Whoops. But this part is not, and so on. So I look at this and I say to myself, where on earth do some of these curves come from? They come from the algebra of projection, but geometrically I have no intuition at all. So, Pooh Bear once said, the more I learn, the less I know. And that's very much true in this field. However, I have learned a few things. The first is that there's more than one way to state a problem. Obviously they're equivalent in terms of decidability, but not in terms of practical computability. I hope I've shown you that today with the enormous differences in running time. So if Icai is about bridging the gap, I hope I've done some of that here. The differences are vast in practice, yes. We have some reasonable heuristics. We need to do much more work on the theory, on the experiments, and, I claim, on the software packaging. This is not yet at the state where I can connect it to a solve button, which is what you want to do. And, just as a challenge to other researchers, it would be nice to have some practical work on the alternative methods I've mentioned for quantified elimination that are doubly exponential only in the alternations. But that work, while brilliant theoretically, appears not to have led to any practical work yet. Thank you.